All right, let's do a little section 7.9 here. So we're still going to be dealing a little bit with limits and stuff of that nature. So what we're going to do is we're going to look at infinite limits. So in the past, we have looked at the definite integral from a to b of f of x with respect to x. If we can take the antiderivative, which we call capital F of x, we were going to evaluate that from a to b, and that ended up being one of the second fundamental theorem of calculus. Antiderivative evaluated at b minus antiderivative evaluated at a, right? So we did that back in Calc 1, so that was kind of a fun way to do it. So what are we going to do here now is we're going to look at infinite limits. By the way, what did this represent? If we had a continuous function, let's just kind of remember what that represented. If f was entirely on or above the x-axis on that closed interval a to b, and it was integrable, meaning we could take the antiderivative, what did that definite integral give us? I just drew a picture of it. Area under the curve, right? Between the curve and the x-axis. So if it's entirely on or above the x-axis and it was integrable from a to b, if f is, then this definite integral from a to b gave us that area under the curve. Well, what if I have something like this? What if I have something like the definite integral of, or excuse me, what if I want the area under the curve f of x equals e to the minus x from 0 to infinity. Okay, well, what's that going to look like? So e to the minus x is a flip. Instead of going up this way and exploding to the right, it's going to explode up as we go left, right? Because negatives become positive and positives becomes negative. So it's a rotation about the y-axis of y equals e to the x. We just talked about exponential functions there. So really what we're doing, and we cross when x equals 0, f of x equals 1, f of 0 equals 1, right? So basically I'm gonna keep going. I'm gonna draw this out a little bit farther, but I get closer and closer and closer to this x-axis without touching it, right? And so the reality is, can we calculate that area if we keep going out to infinity? Would it exist? Would it converge on an actual number, right? So it is possible that since you go out forever and that you always have space when you zoom in or magnify in between the function and the graph and the x-axis, it's possible that you might have infinite area. But it's also possible that because it gets so tiny out there that this would actually converge on an actual number for real area. So the question is, how do we do that? And so the way we're going to do this is, first of all, we got to make sure that we can take the antiderivative, but we're going to have some theorems here. So this is one theorem. We're going to let f be continuous. So for this theorem, we need continuity. So let f be continuous for all x is bigger than a. Now in this case, my a was 0. I'm starting at 0, but I could start at 5 if I wanted. It's the lower limit. So f is continuous for all x is greater than a. Then what we're going to do is, if I have this, basically we're going to take a definite integral from a to positive infinity, right? Is essentially what I'm doing. That's kind of the concept of what I'm doing. F of x with respect to x, we need to know how to calculate this then. What this is going to be defined to be is going to be the limit as some b goes to infinity. And then I'm going to turn this into something I can handle, the definite integral from a to b of f of x with respect to x. Okay? So basically, if I have what I call an integral with an infinite limit of integration up here, this positive infinity, I need to rewrite it. Okay, and I can do that as long as f is continuous for all x is bigger than that lower limit. So as I go to the right, which is essentially what's happening here, I can rewrite it like this. So let's actually look at this. If I've got f of x equals e to the minus x, or 1 over e to the x, how would I do that then? I would say that so for the example we have, if I want the definite integral from 0 to infinity of e to the minus x with respect to x, this is going to be equivalent to the limit. And since normally we go from a to b, we just call it b goes to infinity of the definite integral from 0 to b of e to the minus x dx. Okay, so I need to figure out what this is. So this is something that we can handle from back in chapter 4, right? So if I do that, once again, we're going to take that limit last. So leave the limit on there until you take it. So what's the derivative of what is e to the minus x? The derivative of e to the x is e to the x. But then this chain rule, you got to take the derivative of the exponent. So this would be minus e to the minus x, right? Because if I take the derivative of e to the minus x, it's e to the minus x times the derivative of the exponent, which is minus 1. I don't have the minus 1 here, so I put it here. Everybody good with that? I haven't taken the limit yet, but I am going to evaluate this from 0 to b. Okay? Now, if this limit exists, that's going to be this area. Okay? And then we would call this a convergent integral. All right, so let me go up here then and keep going. So this is going to be the limit as b goes to positive infinity, of minus e to the minus b, and then it's upper limit minus lower limit, so minus e to the minus 0, which is just 0. Of course, what's e to the 0 power? 1. Okay. So this is plus a plus. So this is going to be the limit as b goes to infinity. I'm going to just rewrite this a little bit. And this is minus e to the minus b. I'm going to write that as minus 1 over e to the b power plus 1, right? Everybody good with that? Just doing a little algebraic simplification. Now I can go ahead and let b go to infinity, and what's that equal? If I let b go to infinity, what do I get? This is minus 1 over infinity, right? The bottom gets huge, so this goes to what? 0, right? So what do I get for the actual true area under the curve from 0 all the way out to infinity? This actually converges to an area of 1 square unit. So that's pretty cool, right? It's not hard, but the concept is pretty easy. So these are improper integrals is what we're looking at. So they're called improper integrals. Okay. Now, we could also go the other way as well, but what did we really need to have? We needed to have a continuous function. So once you get out past your starting point, your function needs to be continuous. Now, this actually represented, because the curve is entirely on or above the x-axis, that actually was equal to the area. It is possible that you have stuff underneath the x-axis, which the area would be considered negative when you're doing the definite integral, right? So don't forget all the chapter 4 stuff that we did as well. Okay, so let's look at another example. But before I do, let's do the other part of the theorem. So theorem, if f is continuous, basically left of b. So for all x's less than or equal to b, which is going to be the upper limit, then the definite integral from minus infinity to b. So if I want to extend and go all the way left, we get a very similar thing, right? Of f of x with respect to x is going to be equal to the limit as, now what do I want to call, what do I want to put here on the bottom? What letter do you think? A. So we're going to take the limit as a goes to negative infinity, because normally we go definite integral from a to b. So if you're replacing the top side, have it be a b. If you're replacing the bottom side, have it be an a, because that's what we had before was the definite integral from a to b of f with respect to x, right? So we're going to take the limit as a goes to negative infinity of the definite integral from a to b of f of x with respect to x. So we have this one as well. And once again, what do we need? We need continuity. We need to be able to draw this thing without lifting our pen left of, in this case, left of b, because that's where I'm going. I'm going all the way to negative infinity for the x values. Okay? So we have that. And then I'll do one example of this. And then we also have one more theorem where we can go from negative infinity to positive infinity. So I'll get that up here too. All right. Anyway, so let's look at an example of this. And by the way, if that limit exists, let's note this first. If the limit exists, we say the integral is convergent to that specific value. If the limit doesn't exist, DNE does not exist, we're going to call that divergent. The integral will be divergent. It would diverge, right? So let's look at an example. What if I have the definite integral from negative infinity to 4 of 1 over 8 minus x quantity squared with respect to x? How could I rewrite this? I want to replace the lower limit, right? With what letter? A. Okay. So it's going to be the limit as a goes to negative infinity of the definite integral of a to 4 of 1 over 8 minus x quantity squared dx. Now, this is okay as long as f is continuous. Left of what? Left of 4, right? Is it? What's f of x? One over 8 minus x quantity squared. Where's this continuous at? Where's it not continuous at? That might be easier. 8. At x equals 8. So it's continuous if x doesn't equal 8. You plug in 8, you're dividing by 0, right? But basically, this is a 1 over x with a right shift, right? Because when you plug in 8, so basically I'd have a vertical asymptote at 8, and it would look like 1 over x right there, right? So basically what I'm doing, I'm going from 4, from x equals 4, and then going left. And ultimately, I'd be trying to see if I can get the area under the curve, right? So that's a base graph shift. But anyway, I'm continuous. It's a rational function, so rational functions are continuous on their domain, right? The domain of f is all reals except for 8. Or from negative infinity to not including 8, union not including 8 to positive infinity, right? So we're good here. That's the whole point. f is continuous. So I can go ahead and rewrite it this way and then evaluate and see if it converges. So what I got to do is I got to do this first. Well, now we're back to chapter 4, taking antiderivatives. How am I going to take the antiderivative of that? You could ask yourself, well, the derivative of what is 1 over 8 minus x quantity squared? That's not too easy. So what are we going to do? What tool? What trick are we going to pull out of our magic hat? Anyone? Anyone? Bueller? Bueller? Come on. Take the antiderivative. Don't worry about the a and the 4. How do you take the antiderivative of that? I'll tell you what I don't like. I don't like that. Wouldn't that be a lot easier if it was something like a you or a y'all? Wouldn't that be easier? Okay, so how about this? So we're going to let u equal what? 8 minus x. We're going to use substitution. So then that's going to be 1 over u squared, which I could write as u to the minus second power, and then I could use the power rule, right? So what's du equal? Minus dx. Minus 1 times dx, right? So if I'm going to rewrite this part in here, I'm going to go back up top, give myself some room. I'm going to get this. Now it's going to be equivalent to the limit as a goes to negative infinity of the definite integral of I don't know to I don't know, right? Because I don't know, I'm changing the variable. So x goes from a to 4. I don't know what u goes from unless I plug it in here. So I'm not going to do that yet. But anyway, it's going to be minus du is minus dx. So minus du equals positive dx. So I'm going to put in a minus du. So I'll take that minus out front. I got my du. And instead of 1 over that thing squared, it's 1 over u squared. So it's minus the integral of I don't know to I don't know of 1 over u squared du. Right? Which I can rewrite 1 over u squared as what? U to the minus second power. So what's the antiderivative of that? So its limit as a goes to negative infinity of what? What's the antiderivative of u to the minus second? Power rule, add 1, divide by that. U to the minus 1 over minus 1. Evaluated from, I don't know to I don't know. Right? But it's this. And of course, if I do this, how can I rewrite? I'm just going to rewrite that. That u to the minus 1 can drop down. So this is like, and then you got a minus sign. So it's minus 1 over u, right? That's what that looks like. If I'm just using algebra. So here's what I'm going to do. I'm going to now back substitute. And if I back substitute, now I've got the limit as a goes to negative infinity of minus 1 over, what was u? U was 8 minus x, right? And I'm going to evaluate that from the minus sign was here. So that's where I got the minus sign. Oh, yeah. So did that cancel it out? I think so. Yeah. Because the antiderivative of u to the minus second is u to the minus 1 over minus 1, but I forgot the minus 1. That was out here. Yep, you're right. Easy fix. Thank you for catching that. So it's going to be a positive 1. Yep. Okay. Now I'm going to evaluate this. I'm not taking the limit till the end, right? But I'm going to evaluate this from, what was my limits? A to 4. Right? So then the rest is just algebra. So this is going to equal the limit as a approaches negative infinity. So now I'm going to plug in 4, figure out what that is, plug in a, figure out what that is, and subtract them, right? So if I plug in 4, I get 1 over 8 minus 4, which is just 1/4 for the upper limit, right? So that's easy. Minus the lower limit. If I plug in a, I get 1 over 8 minus a. Everybody agree? And then I got to take the limit as a goes to negative infinity. So now I'm going to say let a go to negative infinity. You could show that. Now I'm taking the limit. But if a goes to negative infinity, 8 minus a minus infinity is 8 plus infinity. What's 8 plus infinity? Infinity. And what's 1 divided by infinity? 0. It goes away, right? You're dividing by something bigger and bigger and bigger on the bottom. That goes to 0. And so what do I end up with? 1/4, right? So what type of integral is this? Was this? It's a convergent integral. And actually, it is representing the area under the curve of from 4 to the left of f of x equals 1 over 8 minus x quantity squared. This is actually equal to the area of the curve that extends left to infinity. It converges on 1/4 square units. Okay, so that's kind of neat, isn't it? So now we don't have to stop. We don't have to be bounded on both sides. In this case, we've looked at 2 that we're bounded on each side. But what if we're not bounded on either side? Could we do that as well? The answer is yes. But before I give you that theorem, let's think about it a little bit. We had a theorem in chapter 4, antiderivatives. If I had the definite integral from a to b of f of x with respect to x, and I wanted to split it up, how could I split it? Pick a number in between a and b, right? So my interval is including a to including b. If I wanted to split this into 2 different integrals, let's say some of that graph was above the x-axis and some was below the x-axis, and it split from above to below at a certain value where it gave it 0. Let's call that c. I could split this up from a to c of f dx plus the integral from c to b. Remember that? Remember that rule? If c was where c was in between, strictly in between a and b, we could do that, right? We could split it up. And then if I wanted true area, for example, if this was going to give me a negative answer, I could take the opposite of it to get the true area. Remember doing that stuff? So now we could do another theorem. Now we have another theorem that says, what if I have the definite integral from negative infinity to positive infinity of f of x dx? So first of all, I need to let f be a continuous function. Where do you think it's got to be continuous?
All reals.
All reals. Continuous everywhere. So on all real numbers. So we need that first. Then we can say the definite integral from negative infinity of f of x dx equals, what do you think I could do? Could I split this up? I go from negative infinity to c. So c's got to be in between negative infinity and positive infinity, right? What kind of number is between negative infinity and positive infinity? any number, any specific real number. So C is any specific real number, right? You can pick 1,000,000, you can pick a Google, you can pick 0, you can pick -5, whatever, right? Any C is going to work. As long as it's continuous everywhere, we're good. So this is going to be, I'm just gonna draw the in-between one for you real quick, but I'm going to go -infinity to C of f dx plus the integral from C to positive infinity of f of x dx, right? But how would I do this now? How can I rewrite the first one? The lower limit is a, right? So I can rewrite this one as the limit as a approaches what? -infinity of the definite integral from a to c of f of x dx. That rewrites the first one. Plus, now I've got the upper limit is infinity, right? The upper limit is b. So I can go the limit as b goes to infinity of the definite integral from c to b of f of x dx. Okay? So that's how we're going to rewrite when you have infinity, -infinity to infinity. Does this make sense? I mean, it just matches what we did before, but now we have an infinite limit. But instead of having it on both sides, let's split it so we just have it on one side and we can use one of the first two theorems, depending on which side you're on. Okay? All good with that? You want to look at an example of that one? We could. About how about 13? 13 looks interesting. Not exercise. We ought to be able to do all the odds and match the answer in the book as long as the book can do them. That's an e to the x one. But we can try it. It's got the definite integral from -infinity to positive infinity, so that matches what we're just looking at, of e to the minus absolute value of x with respect to x. Well, that looks fun. I know how to take derivatives of antiderivatives of e to the x, and I know how to take derivatives of antiderivatives of e to the minus x, but now I got an absolute value thrown in here. Why do they do that? They just like to make my life difficult, don't they? Like Tim does all the easy ones, and then we got to go do odds like this. It's crap on a stick. So what do you want to do? Raise your hand if you don't like that absolute value sign. I was raising both hands, but you can't tell on video. I don't like it, so how I get rid of it? I don't want to call anybody's specific name in here because I want to keep this for future reference. Student A, right there. Where are you going to split this up at? Pick a number, any number. 5? We could. Does that help with absolute value? 0 might be good because above 0, absolute value of x is positive, and below 0, absolute value of x is negative. So you could use 5 if you want, but if I want to tackle what I see as being a problem here, I'm going to split it with 0. So this is going to be equivalent to the definite integral from -infinity to 0 of e to the, okay, now I got a question for you. We need to go back to see what the absolute value of x is. The absolute value of x by definition is x if x is greater than or equal to 0. What is it if x is less than 0? Like if x is -5, what's the absolute value of -5? 5, and then how do I write that here? The opposite of x. So if x is a negative number, you take the opposite of it. So this is just a base definition that we had back in chapter 1 for absolute value for a base graph shift, right? This is one of the first things we learned together in calc was base graph shifts. But this is absolute value of x. So how can I rewrite that? What are my x's here? What are my x's here? Positive or negative? From negative infinity to 0, what are they? They're negative. So how do I rewrite the absolute value of x? So this is minus, what's the absolute value of x? How do I rewrite that? If x is negative, I'm rewriting it as opposite of x, right? So it's minus a minus x. Well, that becomes pretty easy because what happens to those minus signs? Plus a positive, right? So this is just e to the x. Anyway, and then plus, now I'm going to go from 0 to positive infinity with respect to x of e to the minus what? How do I rewrite the absolute value of x if x is greater than or equal to 0, which it is there? X. That's just an x, right? Everybody good with that? And then now I've got two problems that I want to deal with here. And so let me just rewrite it one more time. But now I've also got, besides that, I've got a limit. So I've got those things I want to replace. So this is equivalent to the limit as, what letter am I going to use for negative infinity? A. The limit is a goes to negative infinity of the definite integral from a to 0 of e to the x dx, plus the limit as, what letter am I going to use for that positive infinity? B, right? Limit is b goes to positive infinity of the definite integral from 0 to b of e to the minus x dx. Which we already did this one, didn't we? Wasn't that one? We already did this one. That was the first example I gave you. So this right here equals 1. Rewind the video. Okay. What's this one equal though? We got to figure this one out. So is this also going to equal 1 or do we know? We don't really know, do we? This is 1 over e to the x. Let's figure this out. So this is going to be the limit as a goes to negative infinity of, what's the antiderivative of e to the x? E to the x evaluated from a to 0. Whoa, a to 0. Okay. So that's what this one equals. So this is the limit as a goes to negative infinity of e to the 0 minus e to the a. Okay, well, what's e to the 0? What's e to the 0? 1. And then minus e to the a. So now if I let a go to negative infinity, what do I get? I'm going to get 1 minus e to the minus infinity, correct? And what's e to the minus infinity? It's 1 over e to the positive infinity, which is 1 over infinity, right? So it's 1 minus 1 over infinity, which goes to, if you want to write that out. You don't have to, but this goes to 0. I already had e to the infinity. It's minus 1 over infinity. Anyway, that goes to 0, right? So what does it equal? It does equal 1. It was actually just it's a flip on the other side, but it's the small end of the tail going left. Really, this one looks like this. What's e to the x look like? It looks like that. It explodes to the right. So it's the small end of it's the left side. It's the smaller end under the curve. What's this one? It's flipped, right? So it was it was this way. Did I start at 0 on that original one? I got to make sure I started at 0 and not 1. I think I started at 0. Okay, because if I started at 1, it would not equal 1, right? Or in other words, if this is from 1 to B, or like student A said, 5 to B, it wouldn't equal 1 because I'd be leaving out a chunk of area, which we could figure out what it is from 5 to infinity by doing 0 to infinity, which is 1, and then just take the definite integral from 0 to 5 and subtract it away using chapter 4 methods, right? So we could figure out the area from 5 to infinity, or we could just use this new notation. But anyway, and then what am I doing with both these? I got 1 plus 1, so what does this equal? My answer is 2. So this definite integral is convergent. By the way, they're not all convergent, but this is convergent, and it's convergent to 2. Okay? Any questions on that? You want to do one that's divergent? See what that kind of looks like. Let me see if number 17 might be a decent example. Natural log. We got the natural log. So let's look at it. Anyway, this is nice stuff, right? It's not hard. As long as you can take the antiderivative, it's not hard. But how do we take antiderivatives? We got chapter 4 tools. We got chapter 5 tools. We got front and back flap tools. We got inverse trig, antiderivatives. We got trig antiderivatives. We got hyperbolic trig function antiderivatives. What's the integral of sinh? Cosh. What's the integral of cosh? Sinh, right? So we got all them too. So like we just can't forget about all the different antiderivatives that we've done. And we've had tools for taking antiderivatives, namely substitution, which we've already done today. And then what else? Integration by parts. Integral u dv equals uv minus integral v du. Could we use that with an infinite limit? Or an improper integral? We could. We could use integration by parts. Was there other stuff that we had? Probably. You can go back. You got your whole prior learning modules for taking antiderivatives. So we've done nothing but take a whole bunch of antiderivatives. Calc 2, we took a bunch of awkward antiderivatives. And if we need to do that to calculate these improper integrals, we will. All right, but number 17 is the definite integral from 1 to infinity of the natural log of x dx. Okay, well, let's look at this. What's natural log look like? It looks like this, right? And when the natural log of 1 is 0. So we're going from 1 to infinity. So what am I really doing? This is actually going to come up with the true area under this curve once it hits the x-axis and goes to the right. What do you think this area is gonna be? You think it's going to converge on a number, or you think it's going to keep blowing up? It's going to keep blowing up, right? This goes out and up forever. So it gets taller and taller and taller the farther right you go. So as we keep going, the area is going to continue. This arc, area under the arc is going to get bigger and bigger and bigger. So my guess is that this is going to be a divergent one that goes to infinity, right? In fact, it is. Can we take the integral of the natural log? Anybody know how to do that? The derivative of what is natural log? The derivative of natural log is 1 over x, not the antiderivative. Do we have this one in the front or back flap? Anybody got them formulas? I don't know if we got this or not. We'll just take a little time out right now. We're going to see if we have this. But the reality is we don't need it, do we?
natural log u, or u natural log u minus u.
Okay. So this is going to be equal to the limit as what's the top one? B. Limit as B goes to positive infinity or just infinity. You don't need to write positive infinity because if you just write infinity is positive. The definite integral 1 to B of natural log x dx. And what do you say this is?
X natural log x minus x.
X natural log x minus x. And then that thing is going to be evaluated from 1 to B. So you can do this if you want, but we know that this is expanding without bound from the graph. So we know that this is going to be positive infinity, which makes it divergent. Okay, so there's one that's divergent. But if we go ahead and plug this in, we're going to have B times the natural log of B minus B, and then minus, plugging in the lower limit, 1 natural log 1 minus 1. And of course, natural log of 1 is what? 0. So minus a minus 1 is plus 1 here. And then I've got B natural log B minus B. And then plus 1. All right, so the question is, if I let B go to infinity, what happens to this? It's infinity minus infinity. Do we know what that is? This is infinity minus infinity. Do we know what that is? That's an indeterminate form, correct? Okay, so what could I do? Could I factor a B out and get natural log of B minus 1? I could. And then now this is, what would this be? If I let B go to infinity, so I'm going to factor B out. This is infinity times natural log of B compared to 1 gets huge, right? This is infinity times infinity. So what's that? Do I know that one? What's infinity times infinity? Infinity. So this one's infinity. So this is actually infinity. So I couldn't figure it out if I leave it as infinity minus infinity without looking at graphical methods. And then plus 1. So it's infinity plus 1, which is what? Infinity. So there's the analytic way to come up with it. This was the graphical way. I will tell you this, if I have y equals x, what's that look like? Y equals x is right here. So for b, just the constant function compared to the natural log of b, or x compared to the natural log of x, which one is bigger as you go right? X is bigger than the natural log of x if x is greater than what? That goes through the origin. If x is greater than 0, x is greater than the natural log of x, isn't it? So the natural log is kind of like an anchor on a ship. It's a drag on it. It slows it down on how high it goes, right? But x to any power bigger than 1, like x squared, x cubed, x to the 10th, those are going to explode up too. Those are also going to be bigger, right? So that's just true in general. So moral of the story, to get to the answer, did we have to go through this and find that and search through our log integrals? That's kind of ironic. Didn't have to, because we knew that, because we know what it looks like, that's expanding. The area here is expanding without bound. Okay? But what if it's homework to turn in? Student number the next one. If it's to turn in, would I want to see this to verify it? Yeah, I'd want to see it. Okay, so I'm going to stop recording now. So that's 7.9 in a nutshell.